All right, so beginning our conversation, you will have noticed if you've been on Moodle that I have placed the slides for today's class and future lectures on this topic on the course page, so you should be able to download it and follow along as I am teaching. Today we begin a new topic um, with regards to alkenes and their reactions. I am cognizant of the fact that I do need to upload the recordings from last week's class, and so hopefully I get a chance to do that today. Okay, so starting with what we were discussing at the last session, you will see here that there is a summary table of the E2 parameters and the components that govern the E2 reaction. And so just to bring some closure to that topic, we are here to look at that, and we are able to see that for the E2 reaction, the substrates run parallel to the SN2 reaction. E2 reactions occur on substrates that are first and foremost primary in their substitution, and then secondary substituents, and last of all, tertiary. In fact, the tertiary substrates tend to be least likely to undergo E2 elimination because they are more susceptible to E1. The type of nucleophile or base that is appropriate for an elimination, whether E1 or E2, tends to be strong and large or bulky, and that's because we have already discussed it as being because of the fact that bulky bases have a harder time accessing the electrophilic carbon center. Solvents can be polar protic or they can be polar aprotic. Both will work fine in the E2 reaction, and especially because of the fact that in the case of the E2, you do not have a carbocation intermediate. So what that then means is that both sets of solvents would work well. In the case of the E1, you will recall that you have a carbocation intermediate that benefits from the stabilization provided by polar solvents. Finally, the question of regioselectivity or specificity also presents itself in that, yes, Zaitchev's rule does prevail, and that essentially is the rule that says that the alkene that we get will be the alkene that has the greater level of substitution, the most stable alkene product. Okay? So moving now on to our topic for today, we are at least in a position to begin building our reaction library. And so on the screen, what you have before you is a number of transformations that are able to occur with one electrophile. So in the center, we have our cyclohexyl bromide, which is our designated electrophile. And in this case, it can undergo nucleophilic substitution reaction by having contact with a specific nucleophile. Whether weak or poor, it would yield the product that is in the form of a substitution product, where you can see the nucleophile replaces the leaving group, and the type of product that is formed is reflecting that. Of course, if you change the nucleophile, you are able to change the kind of product that you're able to access. So if your nucleophile is an hydroxy nucleophile or water, then a nucleophilic substitution will allow you to be able to access alcohols. If your nucleophile is an alcohol, then the product that would result would be an ether, because you would have an OR here. If your nucleophile is an amine, then of course the product that you're obtaining from the substitution reaction would be an amine product, and so forth. So you're able to see then that through the substitution process, we are able to gain access to a wide range of chemical compounds by simply varying the nucleophile that is reacting with this electrophile. On the other hand, we have also discussed the competing reaction that is possible in that same set of reaction conditions, where instead of the nucleophile behaving as a nucleophile, it is able to function in its capacity as a base. Now, in that case, it is still considered an electrophilic nucleophilic reaction, except that in that particular case, there is not a substitution that is occurring. The resulting product is the form of, the resulting product actually occurs because of what we call an elimination. And that elimination is prompted by the nucleophile behaving as a base that attacks a proton that is on the adjacent carbon to the carbon that bears our leaving group. Okay, so we have access then to two categories of molecules by actually just subjecting this one electrophile to varying reaction conditions. So to summarize, on the one hand, we're able to access our substitution product. And on the other hand, alternatively, we are able to access alkene products which result from the elimination process. So today's discussion is a discussion that will focus on the possibilities that exist with regards to reacting alkenes. So in other words, imagine if you were to take the alkene that you formed from the elimination product, from the elimination process, and you now wanted to use that alkene to build molecular complexity. You want to make molecules with it. There are a plethora of reactions that you are able to have access to and make use of to build molecular complexity. And in fact, that's what the job of a synthetic chemist is. The person that actually is behind the reactions, their role is to use the reaction pool to sort of create varying combinations of reaction sequences that would allow for molecular construction. And the truth is that that is actually what is taking place in our living systems at all times, in any case. So this is no different. We are basically adding to our reaction pool by now considering alkenes as a starting material for the next set of reactions. So what we know about alkenes is that they have pi electrons. You remember that they are sp2 hybridized carbon atoms. And as a result of that, that sp2 hybridization give the alkene carbons two bonds that are closely associated with each other. Now, we would have discussed in our early stages of this class, of this course, the fact that this double bond is comprised of two types of bonds. They're not one and the same. So there is one bond that we have identified as sigma, and then there's another bond which we have identified as pi. And because we know that these are two different types of bonds, it is fair for us to assume and expect that these bonds will vary in strength. And so it therefore means that in the case of an alkene, when we consider where the bond is breaking and which bond is forming, we have to identify that bond by looking at our bond strength differences that exist within the alkene framework itself. And so since we already know that a pi bond is made up of two parallel p orbitals that both contain one electron each, it is fair for us to understand or appreciate that the pi bond, which exists because of this parallel overlap of our p orbitals, that pi bond is actually weaker than our sigma bond. And since it is the weaker bond, it will then be the bond that is going to take place or participate in reactivity where alkenes are concerned. All right, so the sigma bond, which is at the bottom here, remains unchanged and uninvolved in alkene reactions. All right, so it therefore stands to reason that our pi electrons are the electrons that will be the workhorse, if you will, of the reaction process. And so we are now going to consider reactions where alkenes are behaving as nucleophiles. We already know what a nucleophile is. A nucleophile, just for those of you that don't remember, a nucleophile is a species that is nucleus loving, and that means that it is characterized by having great electron density, or it is electron rich in its nature. And so alkenes are considered capable of being able to conduct nucleophilic reactions because they have access to pi electrons that are available for attack. So as you see here, here is our alkene in the presence of an electrophile that would then undergo this attack to yield an addition product. Now I'm going to put two arrows here because I don't want you guys to get the impression that you have an attack with the E plus and then that's the final product. That's one of the steps. So this second arrow is here to indicate that there's a subsequent step that would lead us to the product that is visible before you. All right, so just to give you an additional piece of information here, once the attack occurs, the resulting product, as you can see, is what we would refer to as a saturated product or an alkyl product, because what it then is suggesting that the double bond is gone. So alkene products and alkyne, not products, but alkene compounds and alkyne compounds are referred to as unsaturated and sp3 hybridized products or alkane products are referred to as saturated. Okay, so going forward, that's the vocabulary that you would be coming across as we proceed, and that's just to give you some understanding of what we're talking about. All right, so moving on. So here, you will notice that there's a designation at the bottom of this molecule referred to as an addition product. And the meaning for that, the reason why this is the designation that is given is because the product that you see here is the result of components being added to the molecule. In the previous case, we had an elimination product, and that was the result of components being eliminated from the molecule. So here we have a different version or a different process that now leads to a different outcome. And so what we are now looking at are addition reactions where alkenes are nucleophiles. And that would obviously mean that we would be bringing in an electrophile from a different place. So addition products or addition reactions are actually reactions that constitute processes that are the reverse of elimination reactions. And so you can see them as being the opposite of an elimination reaction. Essentially, that's pretty much what we can say about it. Now, whether the elimination is E1 or E2 is beside the point. If you want to go to the starting material of the E1 or E2 reaction, the process by which you would have to undertake in order to be able to accomplish that would be an addition reaction. So the conditions would have to be addition conditions. So what our mechanism looks like is essentially first the alkene electrons undertaking an attack on our positively charged or our electron deficient electrophile. And essentially you're seeing that the pi electrons from the alkene are moving away from the alkene towards the electrophile itself. Now what that means is that these two electrons here were being shared between this carbon and this carbon, carbons 1 and 2. And once the pi electrons are removed from being shared between these two carbon atoms, it would then mean that one of the carbon atoms would become electron deficient. And so that deficiency shows up in the form of a carbocation being created at that carbon. Okay? Of course, you observe that in the process, a bond has been formed between carbon C, sorry, not carbon C, but the carbon that is highlighted in red and the electrophile itself. And that's the product that's what is showing up in the product that is before you. Of course, the reaction is not finished because we know that carbocation intermediates are unstable, and so there would have to be a subsequent fast step that will follow. So let's take a look at varying electrophiles, and we're going to start with acidic electrophiles. So in this case, the electrophiles under consideration are our hydrohalides as well as our non-nucleophilic acids, and we're going to see what kinds of products we're able to access through this type of addition reaction. So of course, picking up from the previous mechanism, if we observe our acidic electrophiles, we're able to expect that in an acidic electrophile, we know that the bond is already polarized, which would then put a delta plus on our hydrogen, our acidic hydrogen, and that would put a delta minus on the corresponding counter ion or our conjugate base. And so since the bond is polarized, what's going to happen is this delta plus on the hydrogen would be attracted electrostatically to the delta minus that is engulfed in this pi cloud present in the electrons. And so by now, I guess you are recognizing that all of the reaction mechanisms that we are undertaking proceed by way of electrostatic interaction. There is always a rationale that can justify or explain the process. And so essentially what you need to always be mindful of is the fact that your electrons will always move from a delta minus to a delta plus, or they would move from a full negative charge to a full positive charge. But you will never find a situation where in a mechanism you are moving electrons from a delta minus to a delta minus. And so that would then explain the reason why the arrow moves in the way that it does. So here, because we know that this is a polarized bond, and because we know that the hydrogen has the partial positive charge on it, and we know this because we have an awareness of electronegativity patterns, we then can understand why the attack is occurring at the hydrogen and not at the conjugate base of the acid. Okay? Right, so initial attack occurs on the hydrogen, forcing the HA bond to break, and it then would mean that we have formed a carbon-hydrogen bond. So this is our electrophile that was represented in the previous example. And we now have our conjugate base that is present. And obviously, it is going to take on the next step in terms of rapid bond formation with our carbocation. So of course the carbocation would have formed. We've already discussed that. And once the carbocation has been formed, here is, in this case, we have a specific example where the acid is HBr. And here is our conjugate base coming in to attack at the electrophilic carbocation center. And so essentially, addition reactions entail two steps, where the first step would be attack by the alkene on the electrophile, and then the second step would be nucleophilic attack by the conjugate base on the carbocation center that would have been formed in the process. So here's an example of, besides the HBr example that we just saw, here's an example of a non-nucleophilic reaction or a non-nucleophilic attack using an alkene. So here we have what we would call hydration. And the only reason we call it hydration is because of the fact that water is our nucleophile present. So obviously here is our acid. We do not know in this case what the conjugate base is of the acid, but it is suggesting to us that the existence of water in a large quantity is actually what is going to make the reaction proceed in the way that is demonstrated here. So in other words, let me clarify this and say, let's say our acid was sulfuric acid. Sulfuric acid would obviously have a conjugate base of the bisulfate ion. And that ion, or that anion, is capable of intercepting our carbocation here. But simply because of the law of mass, simply because of mass action in terms of excess, the fact that you would have a greater volume of water molecules present would then be the reason why the product would be an alcohol here and not a bisulfate. Okay? So here we have our alkene attacking first the actual H plus, and we can see that the hydrogen is attached to this carbon. So it's not highlighted here, but of course you see that you've gone from a CH2 to a CH3. Which would mean that our hydrogen would have come from that H plus addition. And that would have generated a carbocation at what was previously the other alkene carbon. And of course, water is ready and available to intercept that carbocation. And remember, this is actually the second step of the SN1 reaction here. We've seen this before. And so by now we know that once you have your carbocation, it doesn't matter if your nucleophile is weak or if it's poor, the reaction will proceed accordingly because the carbocation is so unstable. And so here we have that interception by the water molecule, and then the resulting product is an alcohol. So guys, this is an interesting example because it is showing us that we have a number of ways by which we could access the same category of molecules. So we could envision getting access to alcohols by a nucleophilic reaction. We could have simply had, we could have started off with this electrophile here. Well, let me write it down here. We could have had our tertiary alkyl bromide, and by SN1 reaction, led to the loss of our leaving group to give us the intermediate carbocation. And then we could have brought in water or hydroxide, whichever one. And that would have led us to the same product. All right, but in this case, you are seeing an alternative way of being able to access the alcohol product by simply changing the reaction conditions. So in other words, sometimes what chemists do is they use the reaction that is actually there are varying ways that would cause one reaction pathway or one reaction option to be chosen over another. Sometimes it can be security or safety. Sometimes it can be yield. Sometimes it can be economics. Varying parameters contribute to what goes into choosing the reaction process or reaction conditions for a particular transformation. Okay, so we've said this before, addition is the reverse of elimination. And so here is an example of that being played out, where we start off with an alcohol that could then be subject to E1 elimination in the presence of an acid. Now, if we remember, we could bring an acid here. The acid will protonate this hydroxy group. The hydroxy group will then give us protonated water or protonated OH. So we have that essentially activating our OH, making it into a really good leaving group. It then leaves, and when it does leave, what we end up getting is secondary carbocation. Now we have 3 hydrogen atoms that are able to be deprotonated. And so here, the water molecule that left can now act as a base to kick that out. And this is how you are able to get your elimination. So that's going forward. On the other hand, going in the reverse direction, we have the option now of actually protonating the alkene. And when we protonate that, what we're doing is we add a hydrogen to the terminal carbon, and that generates a carbocation. And then our conjugate base of our acid, which in this case would be water, is able to come in and intercept, leading us to further, leading us to our alcohol product. And so this is the example that I was referring to when I said that addition is the reverse of elimination. All right, so here are some examples where addition reactions are taking place with alkenes. And so you're able to see that you can have an alkene and you react it with a particular acidic electrophile. So in this case, we have cyclohexene being reacted with hydrogen iodide. By way of the intermediate carbocation, we're able to access cyclohexyl iodide. Of course, we can change our hydrogen halide and change it to anything. So we can actually switch this up and change it to HCl. And if we did that, we would have the product as being cyclohexyl chloride. And of course, any change we make would lead us to an actual alkyl halide that would be the result of the actual hydrogen halide that we used. So again, this is the beauty of this reaction, because all we have to do is vary the reagent, and in varying the reagent, we're able to access a variety of products. All right, so here we have an example where you have a regular alkene again. In this case, this is actually propene. And once it is reacting with HCl, here is our intermediate carbocation. And then we have 2-chloropropane as our product. Varying it up a bit, we have a new alkene. In this case, it's varied in the sense that we now have an aryl group or an aromatic group. And the reaction proceeds just as expected. Here is our acid, sulfuric acid. So the first attack would be there, H+, give us our intermediate carbocation, and then that is followed up by interception through attack by the nucleophile. All right, so great. So let's now talk about the regioselectivity of addition reactions. As you could see in the mechanism that I had placed up there before, because you have 2 carbon atoms present within an alkene, it would then stand to reason that there is an option available as it pertains to where your electrophilic hydrogen would go. And so how do we determine where the hydrogen will attach itself to in terms of that addition reaction is actually determined by a rule that is known as Markov-Nikov's rule. So here we have a typical alkene again. This is 2-methylpropene that is being subject to addition conditions using HBr. So we can see the electrophile is being attacked by the alkene and the hydrogen is being added, giving us our carbocation intermediate. So our carbocation intermediate is now being intercepted by the counter ion or the conjugate base of the HBr. And so here we can see that our product has formed in such a way that the bromine is being attached at the tertiary carbon here. However, the other option does exist whereby we can see attachment at a different place. So what happens instead if our hydrogen attaches itself at the internal carbon? In other words, carbon 2. If that were to happen, then it would mean that our carbocation would form on the terminal carbon, and that's a much more unstable carbon. That's a much more unstable carbocation intermediate, sorry. And of course, we expect that it would be intercepted by the bromide and all of that, giving us a primary bromoalkane. But the truth is that it is not a stable pathway. So as you guys are aware by now, reactions proceed by way of the path of least resistance. And so you can identify higher energy pathways by observing the intermediates that are unfolding in those pathways. And of course, once you're able to see that an intermediate is unstable, you are right in expecting that that pathway is not the preferred process by which the mechanism will take place. So it then means that when we compare the two possibilities of where that hydrogen would attach itself, the answer would be the answer actually lies in our observing what intermediates would be forming. So essentially we would have to take a survey of the options, look at our intermediates, and once we recognize the intermediates as being less stable, then we have to rule that path out as the option by which the process would take place. Obviously, we're still doing the same electron pushing. The electrons are moving in the same direction in terms of from source to sink. But what we are looking at here is the positioning, where to put what. So here in the box, what we've highlighted is the intermediate that has been obtained for pathway A, and that's because that intermediate yields us the more stable carbocation, or that pathway yields us the more stable carbocation. We already know that tertiary carbocations are stable compared to primary. In fact, primary carbocations do not form unless they have stabilizing substituents associated with them or connected to them. So it then means that our preferred pathway here, or the likely pathway by which this reaction would proceed, would be pathway A. Now, there's a rule, like I said before, that allows us to be able to hone in on that and summarize that. And that rule is referred to as Markovnikov's rule. The rule essentially says that when you are adding an electrophile to an alkene, the electrophile tends to go to the carbon that would yield the more stable carbocation intermediate. Okay? The product that results from that addition is referred to as the Markovnikov product, and the process is referred to as Markovnikov addition. The other product, which can also form, it just would not form in the same amount, is referred to as the anti-Markovnikov product. So, when other acidic electrophiles such as water are used, it is fair to assume and definitely makes sense to note that the product that you would get is an alcohol. And so just make a note of that, because there's a section on the course outline where we would have talked about, where we would have needed to cover alcohol synthesis or the synthesis of alcohols. And this would be where that comes under. So of course we already did the hydration reaction. The reaction that is on the screen is another set of reaction conditions that show us how to access alcohols. We're not going to do the mechanism of this reaction, but it is important for you to note the conditions. The conditions are Lewis acidic conditions, and they entail the use of mercury diacetate and sodium borohydride. Now, these reagents you would have not seen before, and we know that, but it is important for you to know the reagents so that you can see what your alternative options are as it pertains to how to access alcohols from alkenes. So at this point, you have three reactions that you've been introduced to thus far, one of them being a substitution reaction, and the other two being hydration, and now this third option where we're using the mercury acetate as the reagent mix for alcohol synthesis. In the case of this process, the Markovnikov product is the favored product as well. And this process is referred to as oxymercuration. All right, so at this point, we're going to stop. It is 10 minutes past the hour. I think that you guys would have gotten quite a fill here with regards to alkene reactions. And just by way of announcement, note that this afternoon our lab will not be a lab activity. Instead, we will use the lab time as class time. And so we will pick this conversation up this afternoon in our lab time. Okay, I am going to stop at this time. I'm going to stop the recording and leave the room open for questions.
Hey, good morning, Miss.
Good morning, Tameshwar.
How are you?